Good morning, everybody. Or, afternoon. For you guys, afternoon and morning, same thing. Happy to see you. Today, what we're going to start digging in on is calorimetry. Last time, what we looked on was work, like what happened, like what kind of work was done when there was an expansion or a contraction of gases, like what kind of work was done on the environment. But now it's like mostly W. But today, what we're going to look at is we're going to look at Q, like the change in thermal energy and how we can determine that. It's called calorimetry. It's Q equals MC delta T, my dudes. That's exactly like what we did in Regents chemistry, like almost exactly, with one little thing that's a bit different. But we're going to dive a little bit deeper into some of the specifics of where the energy's going, how it's getting there, and all that kind of good stuff. Whereas in Regents, we were just like, where did the energy come from? I don't know. Where'd it go? I don't care. Oh, Juniper's so cute. Yeah. So, yeah. You guys get what I'm saying? Well, even if not, here we go. All right, that was last time. That was just you guys doing your thing there. Sorry. Here we go. So specific heat. You learn this in Regents. It's the amount of energy it takes to change the temperature of one thing by 1 degree. And here is something that I want to point out here, right? We're going to be using Celsius a lot. However, we're going to use Celsius and we're going to use Kelvin both, right? And they're going to be interchangeable here because, remember, Lord Kelvin based his scale off of Celsius. And what that means is that a change in Celsius is exactly equal to the change in Kelvin. So in other words, if we have a change in 5 degrees Celsius, it is exactly equal to 5 Kelvin, right? Because the Celsius is this big, Kelvin is that big. It just kind of like equals the same. You guys know what I mean? Awesome. That's why we're going to use, like, sometimes I'll use Celsius, sometimes I'll use Kelvin, and it doesn't really matter. I don't really care. I'm going to, like, interchange them because it really, really doesn't matter. Now, this is something a little bit new for you guys, but it's sort of still like the same thing as Q equals MC delta T. We have heat capacity, right? Heat capacity, and this is denoted by a big letter C. Heat capacity for us is, why is this thing so, like, why is this thing so stupidly touchy? Oh, this just makes me... Hold on, guys. I'm having technical difficulties here. It makes me want to, like... Makes me want to poke my eyes out sometimes. Heat capacity. As I was saying, heat capacity of a substance is the amount of heat that is required to raise the temperature of a given quantity of a substance by 1 degree Celsius. Now, here's the thing. This technical definition is like of a given quantity, but this is usually like a thing, right? So a thing will usually have a heat capacity, right? Like our calorimeter will, which is the thing that measures heat change, like that will have a heat capacity. So the official academic definition has like a given quantity of a substance, but like it's like when they say a given quantity of a substance, they really mean by a thing. Does that? I hope that makes sense to you guys. And it may very well, as we sort of like dig into this a little bit further. So heat capacity is C equals mass times S. That's like the, like official, the official definition and whatnot. So the heat absorbed or released is going to be just like this. Q equals MC delta T. Oh, we learned it as C. Today we're going to call it S. So yeah, sorry about that here guys. It's basically specific heat, right? But what we do is if we can take these two things, like if we have a given mass that's like fixed and we know the specific heat of that substance, we take these two things and we combine them into what we call the heat capacity. So I guess if your calorimeter was 1,000 grams of iron, you just take the specific heat of iron and multiply it by 1,000. You know what I mean? But like I said, a calorimeter, heat capacity usually works for a thing like a calorimeter, which is a whole bunch of things. So it'll make more sense once I have like a picture that I can like show you and like talk about. You know what I mean? Yeah. So that's there. We take the mass and the specific heat of a thing or a substance, but really it's a thing. I hate that they say it's a quantity of a substance because it really only works for like a thing. At least that's the way it works in like real life. And again, just to say it one more time, delta T always has to be final minus initial. Always final minus initial. You really can't mess with that. The reason being that if you mess with that, you're going to mess with it being like positive versus negative, and that's important to know if energy is leaving the system or being absorbed by the system. Y'all picking up what I'm putting down? Sure you are, because here we go. Woo woo! Here's a question. Oh, I'm gonna just where should I'll be over here for right now. All right. Oh, that's a really bad choice of color. Let me come on over here, get it different, because yellow on this is not working out. How about dark navy blue? All right, so a 466 gram sample of water. Oh, wait a minute, I have an idea. Water. If it's water, right here, specific heat, 4 point. Whoa, look at that. 4.184. I'll put that there so I don't forget. It's heated from 8.50 to 74.60 degrees Celsius. Calculate the amount of heat absorbed. Heat. This is Q, my dudes and dudettes. Calculate the amount of heat absorbed in kilojoules by the water. Man, I know this one. Look, check this out. We got this right here. This, no, not so much that. This one right here. Q equals MS delta T. I like to say C just because I'm used to it. Q is MC delta T. MC delta T. And T is initial minus final. Dude, we got everything we need right there. All right, so let's start writing it out. Mass is 466 grams, right? That's the mass of water. So my S, because it's water, I know that it's 4.184. It's heated from... and then it's heated to and Q is what I'm looking for, right? So there's all my variables. I'm going to take my equation. I'm going to write Q equals MS delta T. This seems really simple. Can it? Give it time. All right, so mass, very simple, 466 grams. 4.184. And delta T, final minus initial. Man, I have no idea how to work that. I know, I'm just going to write it out here. 74.6 minus 8.50. And I'm just going to type this all into my little, like, handy-dandy, like, computer mathy thing. And I'm just going to, I'll be right back. Oh, yeah, sorry. Here we go. Okay. 1, 2, 8, 8, 7, 8. Oh, nope. Easy. 1, 2, 8, 8, 7, 8. 0.0 joules. But this is regular joules, so I need it in kilojoules. And because we're using the metric going to go, I'm going to take that decimal and go 1, 2, 3, and I'm going to call this 128.8780 kilojoules. Now, let me see here. I've got 3 significant figures, 4 significant figures. Let me see, 74.60. 1, 6, that's 4, probably going to be 3, right? It's 3 significant figures. So I'm going to have to round this to 3 significant figures. Let's call it 129 kilojoules. Dig? You guys follow that? Super easy, right? Easy peasy lemon squeezy. Not even scared. Q equals MC delta T is what we did in Regents. Now, let's check out what a calorimeter is. So what we got here in front of us, this is called a bomb calorimeter. So here's why they call it a bomb calorimeter. These things are actually seriously cool. This whole thing, I'm pointing to the screen with my fingers as if you can see. So let me see if I can get this going on here. I don't think I'm gonna. I just give up. So this whole thing here is what we call. This is called the bomb calorimeter, and here's what's important to look at. we've got a thermometer, and the thermometer is going to measure the change in temperature of the water. We've got ignition wires. You've got a stirring mechanism to make sure that the water stays nice and stirred. And what we've got here, this thing is called the bomb, right? This is the bomb calorimeter. It is submersed in water with like an insulated jacket inside a big container that's also insulated. This should be as vacuumed out as like possible. And this is what we call the O2 inlet. And here's where we put our sample. So the way this works is you put a little bit of something in there, whether it's like a chemical or like a piece of a Snickers bar or like whatever we want to see, how much stored energy there is in there. We put it right in there, and then we basically flush this thing out with oxygen, and then we pressurize. Like, man, we pressurize the snot out of this thing. Super high pressure oxygen. That way there's an excess of oxygen. And then these little guys, these ignition wires, they spark, everything burns. This stuff down here burns like crazy because it is in an excess of oxygen. It's in a pure oxygen environment. So man, about anything burns in a pure oxygen environment. Exothermic. This thing loses all of its energy. This water around here absorbs it, and this temperature or thermometer measures the change in temperature. You dig how that process works? So what that means is that energy comes out of our sample into the bomb, into the water, into the calorimeter jacket, into the stirring rod, into the wires, into this little oxygen inlet valve, into the lid, and also into the thermometer, and also a little bit into this evacuated space, and it can travel through the thermometer and onto this thing and through the stirring rod into here. So energy goes everywhere, all throughout that calorimeter. Where is it coming from? Right? Where is it coming from? It's coming from here. Right? So basically, it's leaving our sample and it's going into two basic things: the water and the calorimeter itself. Does that make sense? You dig? I hope you're digging just a bit, because here we go. So here's the thing: the Q of the system, right? This thing, like, it's gonna be the same. It's like zero, because here, let me get a color that I like, because you know I gotta have good colors. Let's go with stinky green. All right, so basically when this burns, right, when we do this, this right here is where all the energy is coming from, right? It's coming out of the reaction and it's going to go into the water. It's going to come out of the reaction and it's going to go into the bomb calorimeter, right? Because this whole apparatus is going to get nice and warm. You dig what I'm saying? So whatever comes out of here is going to go into here, because the energy of a system has to remain the same, right? So the change in thermal energy of the entire system has to equal zero. Otherwise, the world is gaining and losing energy, and you know, we can't do that, man. In this particular setup that we're looking at here, no energy enters, no energy leaves. It's an isolated system, theoretically. And so what we can say is that that's why we can say that the change in energy, the heat of the system, is going to be equal to zero. Meaning that all the energy that the water and the bomb calorimeter absorb comes from only the reaction, and all of the energy that comes out of the reaction goes into the bomb and the water. Are you guys kind of picking up what I'm putting down for that one? So here's how it works. The energy given off by the reaction, we're going to make it negative because it's leaving this stuff, the sample. It's leaving the sample and it's going into the water and the bomb calorimeter. Those things are absorbing it, so the Q has to be positive for those things. Yeah? And we know, just like the example that we just did, that water, the change in energy for the water is calculated by Q equals mass times the specific heat of the water times the change in temperature. Now here's what's going to be a little bit different. We're going to have a slightly different situation here for the bomb calorimeter. Now the reason why it's going to be a little different is because this bomb calorimeter, like if you look at this Jimmy John, it's made out of all kind of different stuff. Stirring rods, wires, this bucket, this container, the thermometer. There's a bunch of stuff going on there. You know what I mean? So here's how we're going to compensate for that, or like make up for it. This is where we use this. You guys remember that? Right. So what this means is we take this bomb calorimeter and we put a known sample that we know how much energy comes out. We do it 100,000 times. We know exactly how much energy should be coming out of the reaction. We can measure how much energy it takes to change the temperature of our calorimeter by 1 degree, because we calibrated 1,000,000 times. You guys get what I'm saying? So remember, the water, the change in energy from the water comes from Q equals MC delta T. The heat energy change, or the Q, or the change in joules for the bomb calorimeter, come from the heat capacity multiplied by the change in temperature. Isn't that brilliant? It's just simple algebra. Does it make sense? Now this one, it says a constant volume, which is going to be a little bit weird, because all those particles are going to be pushing against the side, and the pressure is going to increase, and that pressure is going to do some weird things. So what this means is that the delta H is not perfectly exactly equal, because any work done can't be accounted for. So it's a small detail, but we can still pretend it's you see how it's like slight, it's close enough that it works for almost all applications. But yeah, there you go. So here's an example of a problem. And move myself down here so I can like read it. Okay, a quantity of 1.435 grams of naphthalene, a pungent smelling substance used in moth repellents. This is what makes mothballs smell like mothballs. Was burned in a constant volume bomb calorimeter. I love calling it a bomb calorimeter. Consequently, the temperature of the water rose from 20.28 to 25.95 degrees Celsius at the heat capacity of the bomb. Ooh, this is new. If the heat capacity of the bomb plus water. Oh, that's easy. Oh, see, they're giving us a cheat, because look, here's what that means. Is that when they say the heat capacity of the bomb and the calorimeter, they're talking about this whole thing. Right, where's my thing? They're talking about this whole thing right here. They're talking about that, both the Q for the water and for the bomb. Which, man, this is the bomb. It's making it nice and easy for us. So if the heat capacity for the bomb plus the water is 10.17 kilojoules per degree centigrade, calculate the heat of combustion of naphthalene on a molar basis. That is the molar heat of combustion. Kilojoules per mole. All right. Heat of combustion. This is what we need. What we need is kilojoules per mole. All right. What's my plan? Here's my plan. I got to get to kilojoules per mole. So for me, step one, I'm going to use Q equals heat capacity times change in temperature. That's super sweet, because look, the heat capacity is right here. 10.17 kilojoules per degree centigrade. And I've got my delta T right there. Does that make sense? Great. Once I have kilojoules, I'm going to just do, I'm going to need to, what I need are kilojoules per mole. So I'm going to go from grams to moles. Of C10H8. You get what I'm saying? Then I will put my kilojoules up here that I got from step number 1. And then I will put my moles of naphthalene down here. And it's going to be spectacular. And that will give me the kilojoules, right? The kilojoules of energy that were released by however many moles of naphthalene that I've got. Easy peasy lemon squeezy. Sweet. Yeah. That's all. That's how that's gonna do. So I thought I had a little bit of space there. I guess I don't. So here, let me. I hope you guys have that like memorized, because I'm gonna need to make some space for myself here. Oh, look at this erasey thing. Erase, 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 and make it go away. Make it go away. Make it go away. Bet you thought you wish you could do that for this class. Nope, ain't happening. You're here for the duration, man. You're just gonna have to learn. Like it. No, I'm not sure. All right. So Q equals heat capacity times the change in temperature. That's gonna be a simple 10.17. I don't know, man. I'm gonna use a calculator for this one, because I'm gonna get it wrong if I try to do it in my brain. What is it? 25.95 minus 20.28. Ooh, I noticed. I'm noticing that I'm getting a positive delta T of 5.67. Did I do that right? Oh, that's right, because this is the heat capacity of the bomb calorimeter in the water, not of the naphthalene. Oh, that makes sense, because we would expect all the energy to come out of the naphthalene and into the calorimeter and stuff. So I guess it's good that the temperature is going up, not down. And so my Q, or my kilojoules, and what's really good to note here is that this is kilojoules per degree centigrade, and then times degrees centigrade. They are going to cancel out. We'll be left with kilojoules. So my dimensional analysis pans out. Let's do 10.17 times 5.67. Where am I at? 57.6639 equals approximately 1, 2, 3, 4 significant figures. 1, 2, 3 significant figures. That's going to be 57.7 kilojoules. Super sweet and easy. God, I should do this for a living, don't you think? You better agree with me right now, because you know what I'm saying. All right, so now what I need to do is I'm going to need to go from 1.435 grams. I'm going to put that into the lines of pain. And what did I figure out? 128.2? 128.2 grams per mole. Where did I get that from? Gram formula mass, my dudes. C10H8, 10 times 12 plus 8. That's 120 plus 8, and some decimals because it's hydrogen. There it is. I can't remember off the top of my head, but there it is. So let's math it out. 1.01119. Oh, that's plenty. Moles, but look, I've got 1, 2, 3, 4 significant figures. 1, 2, 3, 4 significant figures. So let's call this 1, 2, 3, 4. Yeah. Great. Next thing I need to do is we're going to do the final kilograms or kilojoules per mole. So I've got 57.7 kilojoules. I'm going to divide that by 0.01239 moles. My final answer is 57.7 divided by 0.01239. Boy, I hope this is right. 5156.389. 1, 2, 3. 1, 2, 3, 4. It's going to be all right. So what I did here is I rounded to 3 significant figures. I did not include a decimal to indicate that the 0 is not a significant figure. 5160 kilojoules per mole. Some serious learning right there, isn't it? Right, so here's what this is. A lot of people ask, like, what's the difference? Like, they see calories and kilojoules. You'll see calories as like a leftover from the olden days of doing calorimetry. Calorimetry, calories, because that's how they used to measure energy, right? In calories. And then what they did was like 1 calorie, like this is what they used to measure energy in, but like nobody wanted to look at how many calories were in an apple of like 50,000 calories or like that didn't make any sense. So what they did was they took 1,000 like science calories were equal to 1 food calorie. Does that make sense? Then like the System International got together. Everybody's like, okay, we are going to go to the metric system, like System International Science System, and now we measure energy in joules, right? And so 1 food calorie is equal to 1,000 science calories, which is equal to 4,184 joules, or 4.184 kilojoules. Do you dig what I'm saying? So one food calorie is approximately 4 joules. So 1 apple, like just to give you an idea of like what kind of energy we're talking about when we talk about like kilojoules, an apple has about 2 kilojoules. Serving of beef, about 8. Do you guys get what I'm saying? Ooh, butter, dude. That's why, that's why butter makes us all like So, man, that's why we love butter, let's be honest, because it's so freaking delicious. It puts out so much energy. That's why. All right. So if we want to get an actual measurement of the real energy, like given off by a sample, this is what we're going to use: constant pressure. I point right there. See that? Constant pressure. Somebody gave me a camera. They shouldn't have done that. Anyway, so here's the deal with this one. With constant pressure, as you can see, this whole system is kind of open to the atmosphere, and this is more like what you saw in Regents chemistry. I know it's highfalutin, isn't it? It actually does some really good, like an accurate measuring of like changes in heat. It's literally just two styrofoam cups with a styrofoam lid, thermometer, and some like thing that acts as like a stirring rod. This is the exact same as a constant volume, right? So the energy of the system here is going to be equal to energy of the water and the energy of the calorimeter and the energy of the reaction. So the reaction is going to give energy to both the calorimeter and the water. But what's really neat about this setup is that the amount of energy gained by the calorimeter is usually negligible. In other words, it's so small we can just like ignore it. I mean, dude, it's styrofoam. Man, it takes like absorbs almost zero energy, almost like practically, like so little we would never notice it. So we like this because it helps us sort of like kind of helps us out with the math a little bit, and because it's open to the atmosphere and it can expand or contract if it produces gas, we can actually calculate the real, actual, precise heat of reaction here. Oops. No heat enter or leaves, but matter can. That's kind of the clutch part. So again, just like before, the total energy of the system has to remain the same. You can't gain or lose energy because conservation of energy. So just like what I said before, is that the energy that goes into the water and the calorimeter comes out of the reaction, or vice versa. You know what I mean? So as long as they're opposite signs, it kind of doesn't matter how you talk about it. Just like before, Q equals M S delta T, and the energy from the calorimeter is the heat capacity of the calorimeter times the change in temperature. And like I said, with things like this, this right here, the heat capacity of our calorimeter is typically so small, like we can just call it like it's really close to zero. So we can usually just like ignore it. Does that make sense? And because it's a constant pressure, not volume, things can expand and contract and like do what it wants to do. All right, here is another example. This is literally what you did in Regents class, but instead of like pellets, you had a bar where you have lead. Also, I didn't give you lead because I don't really feel like poisoning you guys. So a lead pellet having a mass of 26.47 grams at 89.98 degrees Celsius was placed in a constant pressure calorimeter of negligible heat capacity. See, this is pretty nice to have right here, right? So we can just ignore the heat gained by our little calorimeter thingy right there, because you know who wants to be bothered with details? Not me. Containing 100 mils of water. Now you guys remember, because you're chemistry geniuses, that by definition one milliliter of water is equal to 1 gram of water. So 100.0 milliliters is equal to 100.0 grams of water. And why do we need to know that? Because in the equation, Q equals M S delta T. I don't know why it keeps doing that. Oh, I'm left-handed. That's probably why it's doing that. This is mass, so you have to use grams. Dig? Awesome. Next. The water temperature rose from 22 to 23.17. Let's figure out our delta T right now, just because I don't really want to do it again later. Final minus initial. Oops. 0.67. What is the specific heat of the lead pellet? All right, so this is going to be a one-shot deal here of Q equals M S delta T. A lead pellet having a massive constant pressure calorimeter, negligible heat volume. Wait, is it? Oh, wait, of course it will. First, I'm going to go do Q equals MC delta T for the water. Right? Because if I take this really, really hot piece of lead and I plunk it into the water, and here's my little lead pellet, right? All the heat from that lead pellet is going to go out into the water, right? Little bits of Q, little bits of Q, little teeny bits of Q, little teeny bits of Q, right? So all the Q that went into the water came from the lead. Does that make sense? So I'm going to do Q equals ms delta T for the water to find Q, right? That tells us the amount of water or the amount of energy that was absorbed by the water, like by, when the lead was cooling off and giving all its thermal energy into the water. And then for step 2, we are going to do Q equals ms delta T for the lead to find S. You guys picking up what I'm putting down there? All right, 2 steps. Q equals ms delta T. Let's see if we can put this together. So Q equals 100. 4.184. Oh, I can't remember the delta T because I can't remember anything. 0.67. Oh, this is water. All right, so Q equals, check it out, 100 times 4.184 times 0.67. All right, I got 280.194. This is regular old joules. Let's keep that. Let's remember that because our S is joules per gram. So we just don't want to assume that we have kilojoules. So that was step 1 for water. For step 2, now we're gonna have to do this we're gonna have to do a little bit different here. We're gonna do Q equals ms delta T for the lead. So this time, what is it? 26.47. Okay. Right? Because the amount of energy that came out of the water is the amount of energy that's going into the lead. Man, I literally have the memory of a chipmunk, 26.47. S is what we're finding for the PB. Now the delta T, I know what the final is going to be, right? So delta T is final minus initial. The water temperature started here and ended here. So this is our final temperature of both the lead pellet and the water, right? So the water started at 22.5 and it went to there. The lead started at 89.98 and ended at 23.17. So it's going to be final minus initial. In this case, it's going to be 23.17. Where'd it go? I remembered it was 89.98. So it went up. So all right. So I'm also going to be honest with you. There's going to be a little bit of a sign thing here, right? So this is losing. So that was positive. That means that this is going to have to be negative because this represents. So if it's positive here going into the water, that has to be negative there. You're right. So that way, this negative here is going to cancel out that negative there. It's semantics, but it helps to pay attention to those things. So let's see what this is going to equal me. So the specific heat for lead is going to be equal to negative 280.194 divided by 26.47 times let's just hang out with me for a bit here. My calculator's a little busted up. So let's see how many significant fingers. Blah, blah, blah. I think we had how many? Oh, two significant. This is going to be our real limiting thing. Our two significant figures. But then we came up here, so this is going to be only going to be 2, 2. Joules per gram. Yeah. Awesome. Whew, moving on, you guys. All right, let's read this one up here. A quantity of 1.2. So that's just 100, but what this is, it's 3 significant figures. So we can also call this way up here. I'm going to call this 100 grams of a 0.5 molar HCl is mixed with 100 mils or 100 mils, 100 grams of 0.5 molar NaOH, and it consists constant pressure calorimeter of negligible. Oh, that's I love seeing that. The initial temperature of the HCl in each solutions was the same, 22.50, and the final temperature of the mixed solution was 25.86 degrees Celsius. Calculate the heat change for the neutralization. Well, that's nice because neutralization is a 1, right here. We got a 1 to 1 to 1 to 1, so everything's going to be a 1-to-1 ratio. Assume that the densities of specific heats of the solutions are the same as water, 1 gram per milliliter and 4.184. All right. Let's think this one out. So what I've got is, so what I'm going to end up with is I'm going to basically have a 200 gram solution, right? Because I have this 100 gram solution, I have this 100 gram of solution. We're pouring them together. We're going to have 200 grams of solution, right? I don't know if you can hear Wilder back there. He's watching Woody Woodpecker. He's cracking me up. It's going to start at 22.5 and end at 25.86. That's both of them together, right? So my delta T, let's see here, 25.86. .86 minus 22.5. Delta T is 3.36. Hope you guys can see this. It's a little bit small. Oh, yeah. Specific heat. It's okay, I don't care. It's still 4.184. All right. Assume that the densities. What is calculate the heat change for the neutralization reaction per mole? So, step 1 is I'm going to find Q, right? Which is going to be my delta H. The change in heat for this particular reaction. 2. And then I'm going to find moles. In this case, it can be moles of sodium hydroxide or it can be moles of hydrochloric acid. It doesn't really matter because it's all a 1-to-1-to-1 ratio, right? And I'm going to do that using the equation of molarity equals moles per liter. And I have that for both of them. It's pretty nice. They're both 0.5. That's their molarity. Here's their liters, 100 mils, 0.1 liters. It's going to be easy. Then 3, my last and final thing is going to be joules per mole. Yeah. You guys follow that? Easy peasy lemon squeezy. I hope I'm going to have to probably do a little bit of bouncing back and forth here, because step 1, Q equals MS delta T. So in this case, Q is going to be 200 times 4.184 times, what is my delta T? Positive 3.36. Right? So temperature's going up, so I would assume this is going to be a positive. So let's math that out. Man, I gotta get a better calculator. 2811.6. Three, 1, 2. Actually, I'm just gonna keep it at 4. 2812 joules. About, approximately. All right. So for my next one here, so for step 2, I'm gonna have to find the number of moles, right? So in this case, I know that my molarity is moles per liter, because that's all I'm given, right? I'm given molarity and I'm given liters. The molarity is 0.5 and my liters are 0.1. How did I get 0.1 liters? Well, if I have 100 milliliters, I'm going to take this decimal place right here and go 1, 2, 3. Yeah, you follow that? Oops. Super duper sweet. So let's figure this out. X. Might not even need a calculator for this one. I think I did that right. I'm not even going to check with the calculator. You know why? Because I'm feeling brazen and brasher, people. I'm feeling bold. I'm feeling like I just want to do it. I want to go for it. Now, number 3. Where's my little... Where'd you go? There you go, buddy. And now I just have to do joules per mole. So it's going to be 2812 joules divided by 0.05 moles. This is going to give like approximately, I'm not really sure, 5, 6, 2, 3, 2.96 equals approximately. Oh, how many significant figures do I have in my molarity? That's a good question. Let's go check that out. 0.500. So that's going to be 3. Gonna have to round this to 3 significant figures. 1, 2, 3. 5.62. 5.62 e to the 1, 2, 3, 4. Or I could write 56200 joules per mole. Yeah? You guys follow that? I hope you do, because I really don't want to do it again, because, you know, who's going to pay attention to this? All right, review questions, blah, blah, blah. There's your homework right here. Dig into it, y'all. I know you can do these. You can totally do these. Q equals MC delta T. This is stuff you had from Regents class. I know you could do it, so do it.